record it for people who aren't here. The trends I'm going over: atomic radius, ionic radius, ionization energy, metals versus nonmetals, metallic character, and electronegativity. Okay, let's start with atomic radius. Atomic radius is defined as half the distance from center to center of two like atoms that are bonded together. In other words, guys, it's the radius of one of these atoms. But you can't really measure the radius of an atom because you can't really get into the center of an atom. You could measure the diameter, which is actually kind of hard to do. It's actually easier to measure, like, here's one atom, here's another atom. We know where they are. So here's the center, half the distance between them. Okay, that's how it's measured. And that's just a technical thing. What you need to really know about atomic radius, it is the physical size of an atom. It's a measurement of the physical size of an atom. How big it is. Not how much it weighs. How big it is. Its size. Okay? Now, this is not going to follow the same pattern as weight. Heavier atoms do not mean bigger atoms. Alright? Be aware of that. So, the pattern for atomic radius. As you go down the rows, it actually gets bigger. It increases in radius. So the biggest atoms are going to be the bottom row. But as you go across a row, they actually get smaller. They also get heavier. Okay? So neon is the smallest atom in its row. And it is a lot heavier than, say, boron. So neon weighs like 20, whereas boron weighs like 10 or 11, but neon is smaller in size. It's denser. So why does this happen? Well, first off, let's talk about the columns. Let's just talk about a family. Okay? As we go down a family, hydrogen isn't really part of the family, but lithium to sodium to potassium to rubidium, they get bigger. And the reason this happens is because you get more energy levels. So lithium has 2 energy levels. And the one right below it, sodium, has 3 energy levels. So does it make sense that it's going to increase? It's going to be bigger? More energy levels? This one makes sense. So more energy levels means a bigger atom. This is also going to create something called electron shielding. So let me explain what that is. What keeps electrons on an atom? Why do electrons stay on an atom in the first place? Protons. They're attracted to the protons. Like you have positive protons in the center, and electrons are attracted to them, so they stick to the atom. They're going to stick in these energy levels, but that's why they're there. They are attracted to that center. They're attracted to the protons. Now, electron shielding, as you add energy levels, it decreases those outer electrons' ability to stick to the nucleus, because there's so much other stuff in between the outer energy level than the inner protons. So as you add more energy levels, it becomes harder and harder for these outer electrons to stick on the atom. That's called electron shielding. These electrons on the outside in sodium are being shielded from the center by all the electrons in between. They're further away, and there's stuff in between, so they're actually going to be easier to pull off. That's going to become important here in just a minute when we talk about ions. All right? So that's what I'm talking about with electron shielding. Stuff's in the way of that nucleus. Okay? Now, the only reason these get bigger as you go down a column, as you go down a family, is you add energy levels. Across a row, do I add energy levels? No. So everything in the same row is going to have the same amount of energy levels. So this is the second row. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. And I've just taken 3 of them. Lithium, carbon, and fluorine. All 3 of these have 2 energy levels. But as you go across the row, you add more protons. Protons attract the electrons. So lithium has 3 protons. Carbon has 6 protons. It also has 6 electrons, but because it has 6 protons, all of the electrons are more attracted to that center than they were in lithium. So all of these electrons basically scrunch up. The first energy level gets closer, which means the second energy level gets closer. So the whole atom is actually tighter. It's smaller. Does that make sense? The more protons you add, without adding any energy levels, the smaller it's going to get, the tighter it's going to get. So it decreases as you go across a row, across a period, because you have more protons. It increases that pull on the electrons, and so the whole atom gets smaller. So that's atomic radius. That's its size, basically. Next page. You guys want to flip to the next page. Ions. We've had this vocabulary word before. We had it in chapter 4. We talked about isotopes. Isotope is when you have the same number of protons, but you have different numbers of neutrons. You guys remember that? Ions, the other one we talked about briefly. What's an ion? Blank stares.
Charged?
Charged. Why are ions charged? Because the number of electrons is not the same as the number of protons. Okay? You can't really change in an atom, you can't really change the number of protons. Like sodium has 11 protons. This here is sodium. It's got 11 protons. It normally has 11 electrons. As long as it's sodium, it's still going to have 11 protons. But we could take off or add a few electrons. And it's still going to be sodium, because it still has 11 protons. But if I were to actually remove just a single electron here, that one right there, that outer one, is going to be the one that's going to come off the easiest. Take it away, it now would only have 10, and it would have a charge, because it doesn't have the same number of protons as electrons now. So an ion is any atom that either gains or loses electrons, giving it a charge. So let me ask you guys a question. This is losing 1 electron. That means it has 10 electrons now, but it still has 11 protons. Is that going to be positive or negatively charged? Positively charged. Losing electrons gives you a positive charge. Losing electrons gives you a positive charge. That's an important thing to keep in mind here. Charge does not mean addition and subtraction. You take away electrons and you get positive. So positive does not mean plus. Everybody follow that? Positive does not mean plus. I get that a lot. They're like, but it's positive, so shouldn't I be adding stuff? No. Positive means that you have more protons than electrons. Okay? So taking away electrons gives you a positive charge. Adding electrons are negative, that's going to give you a negative charge. Right? So be aware of that. Positive and negative is not the same thing as plus and minus. Right? Now, if I were to take an atom and remove an electron, do you guys think it's going to be bigger or smaller? If I were to take this atom here, this sodium atom, and I remove this electron, just like I'm doing in this little animation, do you guys think it's going to be a bigger or smaller afterwards? Well, I went from 3 energy levels down to 2. There's nothing in this third, right? So it basically doesn't even exist anymore. It gets smaller. So if you remove electrons, it gets smaller. What do you think happens when we add electrons? It gets bigger. Okay? So ionic radius, all the positive ones, the ones that have lost electrons, they actually get smaller than they were before. Whereas all the negative ones, they've added electrons, they're larger than they were before. So I'm going to kind of amend this picture slightly. All right, so here is a lithium atom, or excuse me, a lithium ion. Lithium probably looked about that big before. You guys say it got smaller? Now, when I go to beryllium, beryllium is smaller than lithium. So beryllium was probably about that big before. So we still have the exact same pattern where lithium was bigger than beryllium. The lithium ion is bigger than the beryllium ion. You follow that? But the lithium ion is smaller than lithium, and the beryllium ion is smaller than beryllium. But lithium was bigger than beryllium, so the lithium ion is still bigger than the beryllium ion. So it still follows the same patterns that we did before. All right, it's just all the positives are going to be smaller than normal. All the negatives are actually bigger now. So if we look at, say, fluorine, here's the fluorine now. That's got a negative charge, so it's got an electron added. Fluorine before was probably maybe about that big, smaller. Oxygen, smaller than what I have drawn there. See if I can make that a little bit bigger. Nitrogen, smaller than I have right there, but it's still the same pattern. Nitrogen was the biggest before, and it still is the biggest. It just got bigger. Oxygen was next, and now it's a little bit bigger, but smaller than the nitrogen were that gained electrons. All right, so this is the same pattern as the regular size, but add electrons, it gets bigger. Take away electrons, they get smaller. Okay? So my point here, guys, is that it follows the exact same patterns as the normal atomic radius. And go ahead and write that down. There's a spot for it. Positive ions get smaller. That's because they're losing an electron, so you lose an energy level. So a positively charged ion is going to be smaller than what it was before, smaller than the neutral one. Now negative ions. This ion here, this is an ion, this is normal fluorine. So fluorine normally has 9 protons and 9 electrons. When it forms an ion, it gains 1 electron. So you get 1 more electron added into its second energy level. But it doesn't gain any energy levels. But remember that electrons repel each other. So if you put another electron in that energy level, it actually causes all the other electrons there to push against each other, which causes the whole energy level to actually grow, because they don't really want to be there. You didn't really add any protons to keep it nice and close to the nucleus. You just added electrons. So the whole energy level actually expands, creating a larger energy level. So a negatively charged ion is going to be larger than the neutral atom. All right, next term, ionization energy. So ionization energy is the energy that's required to remove an electron from an atom. Right, that removing electrons forms positive. So this is all about forming positive ions. That's what ionization energy is. Okay? It's the energy to form a positive ion, basically. because removing electrons forms positive ions. So, ionization energy, it's all about the positive. So the pattern here, okay, this is lithium. All right, we've got lithium up here at top, which has 2 energy levels. And this is sodium, which has 3 energy levels. Sodium is bigger. So because it's bigger, the electrons in the outer energy level, are they going to be held as tightly to there? No. So the bigger the atom gets, the more likely it is to lose electrons. The easier it is to lose those electrons. So smaller atoms hold their electrons on nice and tight, whereas larger electrons are a little looser. The bigger you get, the looser it's going to be. That means the easier it is, and so the less energy it takes to pull electrons off. So if we were to go down the column again, this is lithium and then sodium. The next one down is potassium. Potassium's even bigger. That would have even less ionization energy, so it's even easier to pull an electron off. Okay? Which one do you think is more reactive, sodium or potassium? Potassium. It's so easy to pull electrons off potassium that it reacts quite easily. Now, how many of you guys watched the video on alkaline metals and you guys remember sodium reacting? I'll give you a hint. They threw it in water. What happened? It blew up. Okay, it reacted with the water, fizzed around, lit on fire, and then little mini explosion. All right, that was sodium. I would not let you guys do that with potassium, because potassium would be an even bigger explosion, because it's got lower ionization energy and it would actually react faster, which means a bigger explosion. Rubidium. Rubidium's not even allowed in the school. It's classified as a bomb. Cesium. I can't even get my hands on it. Cesium is so reactive it will react with almost anything it touches. I have never held cesium in my hand before, even in a container, but when they sell it to you, they have to put it in a couple of layers of stuff, and it still has a chance of just blowing up for no reason. So, yeah, cesium. Fun stuff. You can get your hands on some cesium. Be very, very careful with it. Francium doesn't even exist on Earth. We can't even really find it. We just know it exists. That's basically what it is. So, the lower the ionization energy, the more likely it's going to lose electrons, and that means the more reactive it is. Okay? So this is what it is like in a family. Okay, it decreases down a group. The outer electrons are further from the nucleus, so they're not held as tightly. Looser electrons are easier to remove, so less energy to remove them. So, in a row, as we go across the row, we already talked about the fact that it gets smaller because you add more protons, pulls those electrons closer and closer. That is the same thing as talking about holding on to electrons tighter and tighter, right? So can you guys see how this is going to go? If it holds on to, say, fluorine tighter than it does in lithium, is that going to be higher or lower energy? Higher energy. So as you go across the row, it's held loose in the bigger ones, so it holds them tighter in the smaller ones. That means it's increasing in energy. Those additional protons pull the electrons in and then hold them on tighter. So it requires more energy to remove electrons as you go across the row. All right, so that's ionization energy. That's about losing electrons. I'm going to skip metallic character for just a minute. I want to jump to electronegativity next. All right, so we're just going to skip one little section really quick. Ionization energy is about losing electrons. Can you guys guess what electronegativity is going to be about? gaining electrons, okay? So, that's why I wanted to skip. It's like, hey, it fits right in with this. Electronegativity is about gaining electrons. It's a measurement of the ability of an atom to attract electrons in a chemical bond. We skip metallic characters, so just go to the electronegativity. I'll come back to it in a minute. Electronegativity is the ability of an atom to attract electrons or gain electrons. Okay? So what electronegativity is, it is a scale from 0 to 4 on how attractive atoms are to electrons. Okay? It is literally like an attractiveness scale. So the higher the number, the more attractive it is, the more likely it is to gain electrons. Right? This is the exact opposite of ionization energy. So you can kind of think of it as like playing in. So if it loses electrons easily, it's not going to gain electrons, right? It's going to lose electrons. Things that lose electrons are not going to gain them because they're losing them. Whereas things that hold electrons nice and tight, they tightly hold on to those electrons, those are pretty attractive to extra electrons. So the smaller the atom gets, the more likely it is to attract electrons and become negatively charged, gain a couple extra ones. Right? So this pattern follows as you go across a row, it gets more and more attractive to electrons. Okay? Lithium has an electronegativity of 1.0, boron 2.0, fluorine 4.0. So as you go across, it gets bigger and bigger, more and more attractive. Fluorine is so attractive to electrons that it will steal electrons from almost everything else in the entire universe. I have never seen pure fluorine with my own eyes, because pure fluorine will react with everything. Literally everything, except for some noble gases. All right? Like, that's about the only thing it will not react with. Pure fluorine reacts with every container we put it in. Like, you can't make a container out of noble gases. You got to make it out of, like, glass or steel or something. And it will react with the container you put it in. So, it is hard to contain it. And then as soon as you put it in there, it starts reacting with the container, and it will slowly build up fluorine compounds on the side, and that's finally what will contain it, is something that's already reacted. That's the only thing that won't react with, basically, is something that's already reacted with fluorine. Like, it's done it, so it's not going to react again. So that's what we got to make the containers out of. Is pre-reacted fluorine things. And even then, you take it out of the container, it reacts with the air. It'll react with people. It'll react with literally everything. So, highly dangerous stuff. But it is the most attractive to all electrons. Okay? Now, you might notice there's a break in this pattern. That would be the noble gases. Okay? Noble gases, if you follow the pattern, it gets more and more attractive as you go across a row until you hit the noble gases. That's because noble gases do not react with anything. Okay? Noble gases do not form ions. They don't form negative ions, which, if you follow the pattern, it seems like they should form the best negative ions, but they don't. They don't form any negative ions. They don't form any positive ions. Noble gases are the last family discovered because they are the boringest family that never does anything, and we didn't even know they existed because they're so dull. They don't react with anything. They're just there. So they don't steal electrons. They don't lose any. They don't gain any. They don't do anything. So you can kind of forget the noble gases for literally almost all of these patterns, except the size one. For ionization energy and for electronegativity, they don't do anything. They don't lose any electrons. They don't gain any electrons. So you can kind of just lob that family off here. So fluorine is actually the highest electronegative atom there is, because it stops at the halogens. All right? Now, as you go down the rows, they get bigger and bigger, so they become less and less electronegative as well. So the least electronegative one is the one in this bottom left corner here, francium. Okay? That is also going to be the one that loses electrons the easiest. These two things are kind of related. All right? Last topic. We're going to go back up to metallic character. Okay? Metallic character is the ability of an atom to lose its valence electrons. Non-metallic character would be the ability of an atom to gain valence electrons. It's basically, instead of having it's more and more ionization energy, more and more likely to lose or less likely to lose as you go around, metallic character is literally just a dividing point, guys. This will lose, this will gain. Okay, so we're basically just like dividing the periodic table. And this isn't the greatest picture of it. So what I want you guys to do is grab a periodic table and look at it. Okay, have a periodic table in front of you. Pull out one of your other ones, not the one that's in your notes. Okay, so here's my periodic table. How many of you guys notice that there is a nice bold line right here? You guys ever noticed that before? That is sometimes called the stair-step line, or it is referred to as the metal, non-metal line. One side of that line is metals. The other side of that line is non-metals. In other words, metals are the things that will lose electrons. Okay? So everything that is a metal will lose electrons and become positive. Everything that is a non-metal will gain electrons and become negative. So this is like the positive-negative division here on the periodic table. So which side's which? Which side has all the metals? Yeah?
With the charge, the right side is negative and the left is positive. Both the metals, the left side is the metals and the right side is...
So yeah, these are all the metals. Right? So they're all the ones that are going to become positive. Whereas on this side of that line, we've got the non-metals. I'm just going to write non. They're all going to become negative. Except, which family? Noble gases. Okay? Not the noble gases. All right? They're technically non-metals. We call them non-metals, but they're the noble gases. Now, hydrogen up here in the corner, if you look, that's actually got like a bold line around it as well. Like it's like box. That's because it's its own little family. Hydrogen could actually fit on either side of the line. Most of the time we're going to call it a non-metal, but it actually could be called a metal. Hydrogen can form a positive, and hydrogen can form a negative. Who did the hydrogen family? Charge is positive 1 or negative 1, right? Positive or negative. It's the one element that can be either positive or negative. All the nonmetals are going to be negatives, and all the metals are going to be positive. Okay? That's what I mean by metallic character. It's the ability of an atom to lose its valence electrons. Can it? Well, if it does, it's positive. Nonmetals, gains. So it's negative. That's the division point.